Do you know that actually the convolutional neural network that has been used with image recognition is a type of regularization of the network because it allows the data to be shared among the networks. That's why it is successful in modeling in capturing variation in the spatial domain because it allows the same weight to be applied throughout to be used in computation throughout the picture. We will see about that next time. Do you know that actually the normal machine learning to be working successfully, it need to have a certain limitations to limit its learning. Otherwise, it will overfit, right? It will be overfitting to the dataset, right? And these are the topics that we will cover today. Lectures today will be about regularization. Regularization refers to the method of regularize or control the model in such a way that the model would learn from the data, but with certain limitations that would limit its growth to to a certain extent that it would not be overfitted, right? Supposedly, but sometimes we can see that if you use deep learning models, the model would easily fit with the data, even though you set regularization because it has such a powerful learning capability. Okay, in when learning, when using machine learning model, either deep learning or just a normal machine learning, the main problem with using machine learning is that we need to have an algorithm to perform well in both training dataset and in the new input dataset. Okay, so the aim of training the model is to make the machine learning model able to produce the results in such a way that the test error is reduced, right? And this technique, this strategy is known as regularization. Now, we have seen in a machine learning lecture that once the learning becomes, the errors, both training error and testing error, will reduce until a certain point that the training error will exceed the testing error will exceed the training error. That means the model overfit with the data. It remembers just a pattern in the data. When the new patterns come in, the model fail to generalize from the learned patterns to answer those questions, those cases. Okay, regularization is used to trying to make the model to be more generalizable, to be able to capture variations that might have similar pattern but not exactly the same with the training dataset that we have. Okay. One of the regularization approach that has been used in many machine learning model is to normalize the parameters by putting in the normalized penalty into the model that we have seen in the derivation of the MAP criteria in the machine learning lectures, and the use of this type of constraint in many model, regression model known as the Rich and Lasso regression. This type of regularization would put in some types of parameter penalties, the parameter norm penalties in with certain parameters, with certain weight adjustment, multiplying with these parameters. And this will be combined with the loss function. That means when the model learns, it will need to take into account not just the mismatch between the predicted data and the actual data. It will have to take into account of this omega function as well. And this omega function will reflect the maybe the size of the parameter that it used. Okay, so let's look at this example. Suppose we have here j j omega as the loss function, and by adding this multiplication, by adding this w, sorry, this is jw, and the w time w. This is like a dot product between vector w, right? Like w square, like the norm of w, to be specific. The gradient of the above function is by taking derivative of this one, you get only w, and this one you get the derivative of gradient, the O1. The update rule then becomes this. Become updating the weight w with respect to this gradient. Okay, so if we were to arrange it a bit, like by combining w and minus epsilon alpha w together, because they are from the same w, what we have would be this one. This one is 1 minus w, right? 1 minus the epsilon alpha w and the gradient, right? The two function. So the new weight would be the combination of this. Now, if we were to considering these two, right? We were considering these two function. This is w square. Okay, this is some types of loss function. When you have the w square, and considering that you might have, suppose you have two parameters, w square refer to circle, right? That means this value w square, it would be because it's like, if you remember, there is like an x square plus y square equal radius square. Right, so the radius is w, the size of this one, and you have the relationship between the w1 and w2 in the weight axis look like this. This would be the error contribution of the weight, and you have error contribution of the loss function. Okay, you have these two. For the L2 in the square case, the L2 regularization case, you can see that this circle, the impact, I would call it the loss, the regularization loss, the weight loss. The weight loss will touch the data loss at this point, right? And this point would be on an arbitrary location on the two axes. What does that mean? It means that the point here will make the value of w2 and w1 low as possible, but not 0. Right? It will make it as low as possible, because you can see that it will not be at this point, but it will be at the touch point here. Right. Now we can see that from the L2, it make the value some types of fraction, some type of point on the two plane. That means the L2 would not give you 0 value. Like it will give you some type of fraction. Why? If we think about the omega as an absolute function, right? An absolute function like this one, then the objective function will become something like this, and the norm level 1. And once we take derivative of this loss function, right? The first one here, because in the absolute you have the, what should I should write like this, right? In the absolute case, you have a function that looks like this. So that means the derivative of this one would be a sine function, right? A sine function that is negative when the value is less than 1, less than 0, and positive 1 if the value is more than 0, right? And then combining this nonlinear function, actually approximate it using approximate this function and the j omega here. We can approximate the above using somewhat linear function, and let's say the analytic solution is quite messy here, but in any case, I think there is a picture there. That's it. In any case, if you considering this, the error occurring from W and the error, the loss function that occur from j omega here, what you have would be different than this one, because now your W loss would look like this. Why is that? Because for the W1 and W2, now the relationship between the values, the absolute values between W1 and W2, the sign will be like a nonlinear line like this one. And the point that this will touch with the boundary, that they will touch one another optimizing together, would be that one axis would become 0, like W1 need to become 0 here, and W2 has some value. This is the effect of L1 regularization, like this. L1 regularization will try to eliminate the value of W, one out of the other. So in this case, if you look at this equation, let me put it here. Here the gradient. Here we have the gradient as sine, derivative, and you have sine. So for it is will be difficult. We can approximate this using the quadratic approximation. So the above here would be the j omega, the same j omega here, plus the quadratic approximation of this function, which become the new weight here, and the difference between new weight and old weight, and plus the original weight. This is like the quadratic approximation is the current position plus the difference between the current position and the next position, and something like the height, and then you kind of multiply the rate of change with the step size, and then you get the actual value of this W of this one. So this is used to approximate the nonlinear function, so that you can take derivative of this and set the value to 0. So by taking derivative of the j omega, the j W here, and set it to 0, you can determine the analytical solution of W, that W has to be this value. It has to be W minus certain this alpha divided by H, which is the gradient, the rate of change, or become 0. Okay, so what does it mean by this one? So there are cases that when you have value of W less than this threshold. When it is less than this threshold, then what happens? This will become negative. When this becomes negative, you get the value equal 0. Okay, that means when the parameter is not important, that parameter will be penalized, will be regularized, so that it will be 0. It will be pushed towards 0. But when the values of W is more than the threshold, then it will not be pushed to 0. It will have some values. Okay, so this is the mathematical representation of the thing that I draw here. Okay, because of the L1 regularization, the L1 regularization, the parameters W, the weight of W, will become 0, or it will become some values, depending on whether that parameters are significant or not significant. Well, simply speaking, L2 will reduce the weight. L1 will eliminate the parameters. Okay, only those that importance will remain. All right. In linear regression model, L1 is called lasso regression, and L2 is called the ridge regression, because you add the L1 and L2 norm to the error function, and it results in this same behavior. Okay, so norm, when we look at the norm function that we add into the model, the function that will control the size of the parameters, when we add this function into the model, into the loss function, we can consider this norm function, the penalty function, as a constraint. Okay, as a constraint, the norm penalty. So what we want is to constrain this lambda omega function to be less than certain value of k, like less than 1, right? Like what we did in the earlier lecture, that we trying to constrain the regularized the linear regression function so that weight is less than 1. The same thing here. Right? In order to do so, we need to calculate the difference between the function and the value of k here, and both when combined would be contributing to the size, let's say the size of earlier the loss function. So if you interpret this, it would be like this function that is containing theta here, which are the parameters of the model. When you subtract it with this k, this would be like measuring the difference between this one and k. So if this value is close to k, right, if this value is close to k, then it would contribute less to the loss. If this value is more than k, if it is more than k, then it will contribute to the loss. If it is less than k, okay, if it is less than k, then it will be negative value, which is good, right? Because we want the parameters to be less than this constant. So by inputting it like this, it will be like we are trying to force it to be less than certain values. Okay. And now this loss function, this Lagrange function, which consists of the say the data constraint and the approximation of the constraint, the solution of this one would be the argument mint, right? The minimum loss, you get theta, and maximum value of alpha, so that you kind of regularize the weight. Okay. So this is the idea of regularization. You want the regularization parameter to have high magnitude, but you want it to have, when you have high value of magnitude here, you want the loss function to be low, okay, so that you get the good data parameters, but having high degree of regularization. Okay, regularization is when it's done with the pseudo inverse that I think I already demonstrated earlier, that suppose that you try to solve linear regression using regularization parameter inside, or in the MAP case, you end up with having this alpha I as adding to the multiplication of the matrix X. Okay, so now it make the problems of constraint optimization becomes the problems of just adding some additional factors into the calculations, and then you can solve it with the same way. Right? Simply speaking, well, regularization will regularize your parameters. You can do it by adding the normalization norm penalties into the Euler function, and the resulting in solving the model will result in adding the terms this alpha I into solving something like pseudo inverse here. Okay, this is how it's done mathematically. Now, how about in terms of the model? In terms of how do you regularize the trained model? You want to train the model using deep learning, but it seems like your model stuck with the local optimum. Your model is always overfit. It might be because the data is not varied enough. Like if you use the data, this OCR data, and then you want to train it with the model, you will find that the variation in the data may not be enough, right? And what would you do? What you can do is to perform data augmentation. Okay, what does it mean by data augmentation? Data augmentation is a method to generate more data. Okay, it's the method that allows you to regularize, to make the model more general by adjusting the data. You are not making the data like a new data from thin air, but what you are doing is to transform the old data into the new data. For example, you can transform these pair of data by deform it a bit using certain transformation into the new one. You can see that 8 were transformed, 3 were transformed. You can rotate them a bit. You can do whatever image processing protocol that allow you to modify with the data. Then you get a new set of data that you can use. Then you can use them into models with certain statistical properties and train the model. So from the few input pair, you can generate the results with the synthetic image, multiple input pairs, and then use them to train the model. And this is a technique called data augmentation. One of my students used this technique to train the acoustic model, to train the speech model by modifying the speech. Well, we have the target, and what we did was to adjust the acoustic speech so that it vary, and then use it to train the model, train the deep learning model with the similar label. So we have like more samples to work with. So this is data augmentation. It allows the model to generalize, not just generating more data, but allow the model to be able to cope with, for example, rotation. Okay, suppose that you trying to model the image like this. Suppose that your data always be the data collected from writing in straight line. Then you can imagine that suppose you rotate the camera a bit, there will be problems. To address those, you can rotate your data to get more data and make the model more generalizable. Like this one. You can perform data augmentation on these cat images, and then doing what? Like doing the F5 transform, rotate them, flip them a bit, putting in noise. These are the things that you can do in data augmentation. That means your data will be, or even put in some patch, say randomly pick part of the image out. Then you get more data to train the model. Okay, this is data augmentation technique. Another data augmentation technique is to inject the data with noise. Okay, you can inject the data. Suppose that you have the training data sets X and Y in pairs. Then you can inject the data into the model by adding noise into Y or adding noise to X. Right? You can adding noise to either of them. Sometimes you can need to add a noise to X because Y is just a label, but you can always add noise to Y as well if it is just a value. Right? And then once the noise is added, then you can train the model using this noisy data. And you have more data set to work with, and also if the model able to learn the pattern, it need to overcome the noise. That means it need to learn how to deal with the noise and learn the general pattern out of this. So my suggestion for those of you who have like few limited data points, generate them out using this technique. It will be useful. This is noise injection process. So from the network model, usually we would do forward propagation, right? So you can do it by adding the noise into the data, or you can do it by adding the noise into the learning, like this. From the model, perform forward propagation, predicting the output, then the noise were randomly added, and then perform backward propagation. Okay. By doing this, like the model has to somehow take into account of this noise that are randomly generated. Right? So it will be more robust in this way. Many paper that if you review the paper that you work as a term paper, you see that many papers trying to regularize their model in different way. Some trying to augment the data by cropping some part of the data out. Some doing something like this, adding additional noise to the data, so that or transform the data into another domain. Okay. Right. All right. This is another way to generalize the data, generalize the model. Is by doing the semi-supervised learning model. Okay. Um, the semi-supervised learning model will be in this way that you have the classifier to make it more generalizable. You train the data by first build the model with the label data. Okay, you have like building the machine learning with the label data. And then you place the unlabeled data with the model and let it predict. Use the model to predict the label. Right. Once it's got the label, then you can fit the model again to get a better. This is called the semi-supervised learning. Right. Train the model first, and then predict. You when the new data that you don't know the label coming in, you classify it into label, and then include it into the training. Okay, which hopefully would make the model again more generalizable. These are, I would say, these are like the strategy that you can deal with the data before using it in the model. But when you review the papers, many times you will see that the aim of a lot of work is to modify the architecture so that the architecture can take care of the generalization problems. For example, there's an architecture called multitask learning. Right. In the multitask learning strategy, you would have input X. This input X will pass through a certain layer. This certain layer will then be used to separate into 1, 2, and 3, and 4 multiple paths of computation. Each of these paths will be correspond to different output. Okay, that means you have multitask. You have multitask and you have a share layer, a share generic layer. Okay, for example, when you create a model to perform image classification, you can use that model that is trained for image classification to adapt to work on, say, object detection, face recognition, to other tasks as well by removing the output. Removing the feed, you see architecture later on, by removing the top part and use the share part in another task, right? So you can think of the above here as a task-specific parameters and share here as a generic parameters. This is one of the idea that allow a lot of technique to work nowadays, like transformer, like embedding. Because you in those model, what you will see is that it contains a certain shared part that multiple head, multiple model share together, and that shared part would learn like a general pattern. For example, if you have the above here to be doing face recognition, object identification, and different things, and you have the share layer on this part, this share layer will learn something like detecting an edge, detecting part of the image. Right? It will learn something that is simple in visual stuff. Okay, so by having share layer, you're creating a generalization layer that need to learn the generalized task. Okay, this is one of the way that can be used to regularize the model. The next one is the one that has often been used because it's easy to implement. This is called early stopping, right? Because you know that if you train the model lots of time in lots of epoch, then the model will become overfitted, right? Like this one, you see that the validation loss slowly increase once epoch increase, and training loss kind of decrease. Decrease repeatedly, but there's a certain point that it decreases, but this does not decrease, right? So early stopping means that you kind of stop the training before you just stop the training early. Okay, I don't actually want to put it into this type of algorithm because, as the name suggested, it's just early stopping. It means that you kind of stop it early. To retain, like you train just a few epoch and then stop. Okay, So you have X and Y as training set, right? Split X and Y into the subtrain and validation to train and validate. And then run early stopping. Start with random parameters and train the model until you kind of having reached the optimal steps, that no improvement, and you kind of stop there. Okay, this is the early stopping task, early stopping optimization, legalization. Another way to perform legalization is to tie the parameters together. Okay, when you tie the parameters together, that say that A and B perform similar tasks, then you tie the parameters of W of A and B together, and then train the model so that it learn from the same weight. Right? So the parameters are tying; they are the same parameters, or they have to be close to one another. We will see this. Well, each of these will be covered later on. Like this one, next lecture you will see this in convolutional network, right? That okay, you have share layer and the other task to perform. In parameter tying, I think there's like parameter sharing as well. Parameter tying means that the error will need to be compute as well in terms of that the weight are not different. And there is another concept called parameter sharing, right? This is a more popular way than tying. That means you use the same parameters. This is used in Siamese neural net. It's used in performing, what's this called? Embedding. Right? It's used in learning the embedding because they are the same parameters and used throughout the model. This is called parameter sharing. Right? It's called parameter sharing. Okay. It reduced the memory use and also it improved in terms of regularization and generalization of the model. Okay. In convolutional neural network, parameters are also shared in different way. Like we have, let's say we have the same kernel. This same kernel is used to compute. The same kernel is used to compute the whole set here. That means the same parameter is used throughout the computation of the whole image, and these are shared. That means it will not be overfitted because it has to learn just like 9 value, 3 by 3 value, 3 by 3 grid, and it will be used to compute the feature map like in layers. Then you can combine feature map into a smaller version, performing convolutional again, and so on to the end. We will see about that next time. But this relies on the concepts of parameter sharing. Right? And you can see that a successful model in deep learning, have a lot of aspects about regularization. Right? And maybe your thesis will be about regularization. By just discovering a way to regularize the model, it might allow you to achieve the task that the research space in that area try to accomplish. Okay. So we have like parameter sharing, parameter tying, and sharing use the same parameters. Another way is to put in some types of sparse representation, add the weight decay, right? Add the weight decay as the penalty of the model parameters. That so that means the weight of the parameter will reduce, and it will make the model more sparse, right? And that's actually I would say the outlandish technique that they kind of just remove the parameters entirely without considering anything, called dropout, and a lot of people use that. Right? But when you think about it, it just randomly prune or remove the parameters. It's funny that people use that and think that this should work. It's like relying on chance, and the model will be pruned out without considering anything. This is more subtle. This one used the weight decay, so there's no the technique here is used the weight decay. So like if you train the model multiple times, the weight would reduce anyway, so the model has to take care of if it's important adding the weight into that point, right? So it's like you creating two forces. Each has to crash with one another, so that it got into like equilibrium, got into the point that the model worked. Okay, so now you see multiple approach, like the approach that based on the architecture, the approach that based on data. If you work on the deep learning project, you can do both. You can do either of them. Right? There are a technique that that rely on the strategy of learning as well. Right? So we look at the way that you can deal with regularization using math, using the learning itself, using data, using architecture, and now using the strategy to learn, right? And the first one is random forest, right? And the technique that used in random forest is called bootstrap aggregating or backing. Right? In backing, you're creating multiple versions of model. Each of these perform the task, and then you combine the result together. This is called an ensemble, right? An ensemble technique. Right? It's quite powerful. That's why random forest is still one of the model that people often choose to use in the real world situations. But if you look at deep learning at the moment, this is still coming because we still do not have a way to easily perform backing using deep learning yet. Okay, the rationale of backing, why it works, is because you are trying to find the expected value of the error, right, of the error square, and this expected value when calculate would equals for the k regression model would equal this. This is the 1 over k. That means if k increase, then the errors would decrease. The expected value of the error would decrease based on the relationship between this one. So the more model you have, the more generalized backing becomes. Okay, but well, as I said, backing works for a small greedy model. Then you have multiple versions. But for deep learning, well, maybe you can find out some papers that try to use backing with deep learning, and that would be interesting in your research paper, in the term paper. This is what I mentioned it, the dropout technique, right? Dropout we would train the model by randomly removing the connection out of the network. That means the results model can be in either of this one. Well, it's kind of randomly removing the weight out, and the remaining has to adapt and work in order to capture the pattern. This is called dropout technique. In the dropout, if you compare the normal technique with the dropout technique, with no dropout, the model will be fully connected. But with the dropout, the model might be a little bit more complicated in the architecture side, but usually it would be less overfitted, right? Harder to overfit with dropout, because you kind of kill the weight out, and then it has to adapt and then utilizing the connection to cope with that missing link. Dropout, and the next one would be a more advanced technique, right? Not Panda. It's called adversarial training. You might know this as the generative adversarial network, GAN, right? The idea is to create the model that is able to generate data, right? That is able to generate data from noise. And you have like adversarial training in order to create the generator that generate fake sample. I will explain this later on. But adversarial training is you need to have like adversarial examples that trying to fool the classifier. So once the classifier receive this, you have like two model, one trying to fool another try to detect the difference. And it results in the improvement of both. And it's called adversarial training, like you have rival and then try to compete with one another. Right? In adversarial training, usually you have this latent space or the noise, and you have this generator network. It is a type of neural network that need to be trained. Okay, this generator network need to generate the fake sample. The fake sample will be switched and with the real sample, and then they will be used to train the discriminator. Discriminator will detect whether you can detect the real sample or not. So the idea of generator is to generate fake sample so that it could fool discriminator. While discriminator need to learn how to tell apart from the fake and the truth, right? So in this case, you have a model, the generator model that learn the data distribution here by learning the latent space, learning the parameters that it need to generate the picture according to the real sample. Okay, this is adversarial training that if you want to train a generator, then once you have generator, you can use generator to generate, say, a specific image that you want. And it will generate like the new image, new data for you, right? And then you can use this to regularize the technique, the training, right? Let's look at the architecture for the adversarial training to perform image recognition. I know it's a little bit complicated because you haven't looked at the CNN, the convolutional neural net yet, but let's try to understand it. So that we will see, okay, this is how adversarial training work. You need to have first the adversarial module, right? Adversarial module here, which contains generator and discriminator. And then you need to have the classification model. This is basically the CNN that we will look at next time, which contain the feature extraction part and the fully connected, the classification part. Okay, how to perform adversarial training? You have the source dataset and the target dataset. Okay, source and the target. This to classify whether you have like which emotion, right? Which emotion here. So in the adversarial module, the source label. Right, the source label here, source dataset, and label is fetched into the network. Okay, and the training dataset put into this part. Then the source label is used to train the generator and discriminator. The idea is of both of these is to trying to the discriminator will try to tell apart the real and fake. Right, between the real and fake, while the generator would try to generate the output out. And these are used in together with the upper part. The upper part is the classification part that you can use. Okay, it's classification part that you can use to train the parameters here. Okay. And it used to train the parameters on the above. Once it is trained, then you can use in the test process. Then you can use the dataset to fetch into the upper part here to perform classification. Right. So the adversarial module here, the idea of adversarial module is to learn to generate the samples. While this one is learned to discriminate, to distinguish between two. They are actually more toward adversarial training, which some parts are not related to regularization. Right? They are related to the trying to create generative model, because once you have generative model, you can use the generative model to make prediction, to generate more output. And even to generate the task that you want, like you can put in condition. Once you say man, then it needs to generate the picture of man. Right? You can do the conditional GAN, right? The C GAN, but that is out of the scope of this. Well, for this one, we are trying to see how different model, how different technique trying to perform regularization. Okay, we see that dropout, remove the weight, messing up with structure, backing, creating multiple version. Adversarial training, trying to generate multiple fake copies from the latent space. So it's basically something like data augmentation in a sense. Okay, in the data augmentation, you have data, and then you trying to augment them, and then use them in performing prediction. Okay. So as you can see that there are many ways to perform regularization. Okay, even now, even in 2021, people are still working on, researchers still actively working on a way to regularize the deep learning, because when you work with deep learning, you can see that it easily stuck with overfitting. Okay, if you give the model too many parameters, it would not perform well with the test data. If you give the model limited data set, it will overfit to just that data set. So unlike human has a kind of accumulative knowledge, so that when they exposed to the new knowledge, they can kind of adapt that to a certain situation and then learn from just a specific pattern. The model is not there yet. So there are many papers that are trying to address the way that you can generalize the knowledge. For example, you can have transfer learning. Use the knowledge learned earlier in different work, right? You can have this embedding in the transfer learning that train it first with different data set, but you can apply it into another, right? So, but if you look at it in the broader perspective, what you will see is that we are still early, right? We are still at the first step that will make like AI, machine learning, and deep learning to be able to generalize. Right now, we put in some type of ridiculous constraint into the model so that it would not overfit. For example, just stop learning, and then it will not overfit well. That's or drop out, like just killing some neuron cell. So go drink some alcohol. Then it will not overfit it. Right? If you think about it in the real world, it will sounds funny, right? Also, it's like what I heard before. Like if you go to sleep, then your brain will kill off some unused neuron, and then it will be better on a new day. Well, probably in that sense. There are still many works that are trying to address the issue of this regularization. And I would say this is the main topics in machine learning. You can do research in this area for, say, the next 30 years, and we're still not there yet. Right? Trying to find a way to combine the knowledge, to combine different patterns, to generalize the different specific pattern into just one, into the same rules. Even, I would say, if you look at it in an even broader perspective, even Albert Einstein trying to find a theory of everything. What is theory of everything? A theory that is can be generalized to anything. Although I don't think there is. But you can see that for the deep learning, just for the AI, the fields of generalizations that I have been discussed here in this short lecture are something that have been attempts in, I say, in the past 5 to 10 years. So these are quite new. And if you want, if you are interested in this area, the way to generalize, to make the knowledge better, to combine the knowledge together, I would suggest that you pick the research paper for study in this class, in this course, in this area. Try to search for the research paper. Then you can ask me whether it's okay or not, but mostly I think it's okay, because it is easy to understand as well, and you can compare it to actual human learning, and you will see how whether it makes sense or whether it's kind of funny, right? That, okay, if you call this the brain, is quite funny that you need to kill brain cell off in order to be able to learn. Right? So this is all for today's lecture. I think what you should learn about, should look at this lecture is not the mathematics, the hard mathematics at first, regularization like that, but in a broader perspective, like in the broader perspective of AI and machine learning, that you can see how important it is for the deep learning process to be able to generalize, and we are still struggling ever since decision tree. We create ensemble, then a forest, boosting, right? Generalize, try to generalize it. Not yet. We create deep learning. Regularization to the deep learning, still not there yet. There will be more, right? in the future, in the development of AI. Just wait and see. You will see that new technique would deal with generalization, would deal with regularization. Okay, and I look forward to the paper that you will bring out and discuss in the class in the latter lectures part that you have to cover. Okay, any questions? That's all for today. Right, it's quite short because when focusing on just regularization, it is important, and you can find many papers about them. But I don't want to just go into the detail. So at least I can give you the idea of the importance of this generalization concepts, and I hope you would pick some of the topic in this area. My students that work on deep learning also deal with this generalization by using the data augmentation, like creating multiple examples and let the model learn. But doing so, when we try to submit the paper to publish in the journal, we encounter that it is very hard to claim that why it works, right? Why the model should be able to generalize in this way. Although we know that it should work for deep learning, but why, right? And why human can do, and why the machine can't. I will leave this to you to think on further. Right? This is important questions, and if you want to pursue the further study in AI and deep learning, think about this. Regularization is the key of the success of AI in the future. Okay. For today's, this is just it. So have a good night. Next time, let's play with CNN and image recognition. Okay? So have a good night. See you next time. Oh, I just saw, sorry, just saw the chat. Individual or group? Well, you don't have to ask. For the master level, there is nothing called a group work. Right? That means research paper that you need to present to the class, research presentation, definitely need to be individual. So pick one paper that you like it can be the topics, any topics in here or outside of the class, as long as they are about deep learning. Okay, that means search for one paper, and then you can if you think topic is okay, it's totally okay, or you can confirm it with me. I think, I don't know. I put in the link so that you can put in the title, the reference into the groups, and reserve the time for presentation here. All right. And this will, because there's no term project, so you need to give explanation about the model that you pick to the class, and we'll see whether what we have there. All right. So the next time, let's look at CNN and see what we can play and see what we can do in terms of the assignment as well. Right, next time. Okay. So that's it. Have a good night. Hope if you have any question, if you have questions about the paper, about this regularization, post it into the group. I will answer it into in the group as soon as I saw that. Okay. So have a good night. See you next time.